So this is a typical area problem you would likely find in a multiple choice section of the AP exam. So we're trying to find the area of the region bounded by the y-axis, the line y equals e, and the function y equals e to the 3x. So to get a better idea, let's try to graph this. So here's our graph. We're going to make y equals e, this line. And now we're going to draw y equals e to the 3x. So it's going to be something like this. It's going to be going up very quickly. And it's going to intersect over here when e to the 3x equals e to the 1, when the equations of the curves are equal. So we can do this solve this by equating the exponents, so 3x equals 1. So this is going to be where x equals 1/3. Okay, so now we want to find the area of this region bounded by this line, and this curve. So that's going to be right in here. And so we're going to take the integral of the formula of the top curve minus the formula for the bottom curve. So let's write that out. We're going to take the integral from 0 to 1/3. Okay, and inside it's going to be a top curve e, and we're going to subtract e to the 3x. And this is all with respect to x. We're going along the x-axis here. And so now to solve this integral, we're going to take the antiderivative of this formula right here. So this e is just a constant, so the antiderivative is going to be e times x. And so now the derivative of e to the ax is a e to the ax. So the antiderivative of e to the 3x is going to be 1/3 e to the 3x. And so this is our antiderivative, and we're evaluating it from 0 to 1/3. So let's plug in those numbers and do the algebra. That's our final step. So first we plug in 1/3. We're going to say e times 1/3 minus 1/3 times e to the 3 times 1/3, so that's e to the 1, so that's just e. That's our first part. And then we subtract when we plug in 0. So minus, this is 0, minus, when we plug in 0 here, we get e 1/3 times e to the 0. Anything to the 0 is 1, so it's just 1/3. We notice this is 0, and we're subtracting a negative, so the answer is just 1/3. And we're done.